Welcome back to your favorite pre-calculus course. We're going to take a look at logarithmic functions. These are inverses of exponential functions. So last section we looked at exponential functions, and in this section, so exponentials like y equals b to the x, right? So if we were finding an inverse, it would be x and the y would be switched, right? So x equals b to the y. So you have two forms of the exponential. One is the exponential form, b to the y equals x. I like to do it this way, b to the y equals x. And then in the logarithmic form, what I do is I write the log, and I write the equal, and I write it this way. I go b to the y equals x, and that's how I remember that. I do it that way. So this one is in logarithmic form right now. Again, there's two forms of logarithms, exponential and logarithmic. This one's in logarithmic form. So let me write it this way. Log of m, log base m of 5 equals 7. And let's put it in exponential form. In exponential form, I would go m to the 7 equals the 5. And that's how I remember that. Let's do this one in exponential form as well. So I would go c to the 8 equals 6. Now this one's in exponential form, so right now it's in exponential form. I'm going to write it this way, 1.4 to the 5th equals q. Let's put it in the logarithmic form. So what I do is I write the log, I write the equal, and how I remember it is I go 1.4 to the 5th, so I go 1.4 to the 5th equals the q. I put the q right there. And that's the logarithmic form. So log base 1.4 of q equals 5. This one here is in exponential form. 2 to the d equals 8. Let's put it in the log form. I write the log, I write the equal, and I'm going to go 2 to the d equals 8. And that's how I remember that. So log base 2 of 8 equals d. One more here. We've got this exponential e to the y equals x. The logarithmic form would be e to y equals x. Log base e of x. And I want to highlight this log base e of x. This is if you have base e, it's also referred to as the natural log of x. So the natural log of x is the same as log base e of x. This is called the natural log of x, natural logarithm of x. Okay. And there's also a button on your scientific calculators for the natural logarithm, so just know that that's base e. So we can do logarithms on our calculator. This is another example, log of 5. Now notice there's no base here. If there's no base, it's base 10. If there's no base listed, it's base 10. So that's called the common logarithm. Common log is base 10. Okay. And so we're going to go ahead and punch log 5 into our basic cheapy scientific calculator, and let's see what log of 5 gives us. Let's pull up our Desmos, and let's punch in. You can go click on functions, and you should see log right there. And by the way, see that natural log, the ln right there? That ln is that log base e that we just talked about. All right, let's do log base 10, log. And we're just punching in 5, log base 10 of 5. Enter. 0.69897. Let's go back to our blah, blah, blah. Round to the nearest thousandth right there. So log base 10 of 5 is 0.699, right? Let's do natural log of 7 now on our calculator. So we go back. Now let's go ln of 7, natural log of 7. Again, that's log base e. So you go to functions there, see the ln, and you punch in the 7. And by the way, you can just do ln, and it'll pick it up. So 1.9459. And we're going to round to the nearest hundredth this time. So right there, 100th position. So 1.95 is what the natural log of 7 is. Well, let's take this and find, now that we know how to go back and forth for logarithms between the exponential form and the logarithmic form, let's go ahead and solve this one for log base 4 of 64. So I'm going to go ahead and I'm just going to set it equal to something. How about y? So if I can find the value of y, I have the value of log base 4 of 64. Okay? So what I'm going to do is I'm going to put it in exponential form. So 4 to the y equals 64. And what would y have to be? I say 4 to the y. What would y have to be? Well, 4 to the 1's 4. That's not it. 4 squared, that's not it, because that's 16. 4 to the 3rd, that's what it is. 4 to the 3rd is 64. So y must be 3. Therefore, we found the value of y. Log base 4 of 64 must be 3. We found the value of y. All right, let's do another one here. We've got log of 1/10,000. We're trying to find the value, exact value, doing this by hand. So again, we're going to set it equal to something. Let's set it equal to y. And if you notice, there's no base here. Well, and like I said, if there's no base, that's base 10. So you can write that little 10 in there. And how we're going to solve this is we're going to put it in exponential form. We're going to go 10 to the y equals 1 over 10,000. Okay? Well, let me rewrite 10,000. That's the same as, 10 squared is 100, 10 to the 3rd is 1,000, 10 to the 4th, right? This is the same as 10 to the negative 4. 10 to the negative 4 is 1 over 10 to the 4th, or 1 over 10,000. So our y must be negative 4. Therefore, so since we found y, our answer is negative 4. Therefore, again, this means therefore, log base 10 of 1 over 10,000 is negative 4. All right, find the value of log 0 on a calculator and round to the nearest 100. Let's go ahead and punch in. Remember, log 0, there's no base, so it's base 10. So I can just punch that in. Log 0, parenthesis. Oh, guess what? This thing is undefined, right? So if you think about this, why is this thing undefined? Well, let's look at it here for a minute. Log of 0. It's asking us to find log of 0. There's no base, so make it a base 10. Find y. Well, 10 to the y equals 0. Well, there's no value that makes that true. Not true. Undefined. Does not exist. Right? And again, on the calculator, same thing. We punched in log of 0, and we get it was undefined. Calculator knows it's also undefined. All right, let's get into some graphing now. So let's take a look at, if you remember, let's go to 2 to the x for a minute. You remember our exponential 2 to the x. 2 to the x had that point 0, 1. This is kind of what that looked like, 2 to the x, right? if you flip-flop all the points, if you were finding the inverse of 2 to the x, if you were finding the inverse, remember when we found the inverse, we flip-flopped x and y. Remember that? So we flip-flopped x and y, and we would solve for the new y. Well, let's just put that in logarithmic form. 2 to the y equals x. So what we have is y equals log base 2 of x. This is the inverse of 2 to the x. So, 2 to the x has 0, 1, has the point 1, 2, 2, 4, 3, 8, and so on. So log base 2 of x would flip all those around. Instead of 0, 1, it'd have 1, 0 right there. Instead of 1, 2, it'd have 2, 1. Instead of 2, 4, it'd have 4, 2. Instead of 3, 8, it'd have 8, 3, and so on. And so you start graphing these points, and you see that in blue that they are inverses. So again, this one is 2 to the x. The blue one is log base 2 of x. So exponentials and logarithms are inverses. And 2 to the x, if you remember, had a horizontal asymptote of y equals 0. So log base 2 of x, instead of y equals 0, would have a vertical asymptote. It'd have a vertical asymptote of x equals 0. The domain of 2 to the x is negative infinity to positive infinity. So the range of log base 2 of x would be negative infinity to positive infinity, all reals. The range on 2 to the x is 0 to infinity. So if you notice, the domain on log base 2 of x will be from 0 on. Right? That would be the domain of log base 2 of x. So that'll kind of get us started on some graphing with these. So let's take a look at this one here. Find the domain of the natural log of 2x minus 7. Write your answer in interval notation. Well, let's go ahead and think about the natural log of 2x minus 7. So let's go to the graphs for a minute. If you think about e to the x, here's e to the x. It's kind of like 2 to the x. Its inverse would be log base e of x. In other words, the natural log of x. Well, the domain of the natural log is x has got to be positive. This domain is x has got to be positive. So that's got to be positive. So when you're finding the domain of the natural log of 2x minus 7, okay, which kind of stretches it out and moves it right a little bit. Okay, it's kind of more like this type of deal. When you're finding the domain of that, what you do is you take that 2x minus 7, you say, well, that's got to be positive. Because I know the natural log of x got to be positive. And then you solve it. You add 7 to both sides. X is greater than 7/2, right? In fact, let's take a look at that graphically so you can kind of see that on a graphing calculator. You've got, here's e to the x, and here's log base e, or the natural log of x. Well, we're going to take that and move it. You know, if you factor out a 2, it's x minus 7/2, so it's right, 3.5? Right 3, sorry. Okay, so you moved it right 3, so there it is, 4, 0, and it goes a little higher eventually. All right, let's go ahead. How about the domain of this one? Well, let's think about 3 to the x. Here's kind of what 3 to the x looks like as a horizontal asymptote y equals 0. So log base 3 of x would flip all those around. This would kind of be what log base 3 of x looks like. And remember, x got to be positive. So when I'm finding the domain of this, I just go ahead and take that, whatever's in there, 6 minus x, and I say it's got to be positive. And then I solve it. When I divide by a negative, don't forget you got to flip that. So this will be x is less than 6. X is less than 6. Okay. That'll be your domain on this. In other words, negative infinity up to 6. That'll be your domain. Okay. Could you do this with transformations? Absolutely you could. If I erase this for a minute, let's think about this. This is log base 3 of 6 minus x. Let me write that as log base 3 of negative x plus 6. Let me write that as log base 3 of negative x minus 6. So the first thing is it reflects it about the y-axis, and then it moves it right 6. Okay, so it flips it over the x-axis like that. I'm sorry, the y-axis like that in green. Then it moves it right 1, 2, 3, 4, 5, 6 right there. It looks like that. Okay, so instead of a vertical asymptote at x equals 0, it has a vertical asymptote at x equaling 6. And so you can see this one that I just outlined in black has a domain that comes from negative infinity up to 6. In other words, x is less than 6. That's how you could do that with transformations as well. Okay, but it gets kind of hairy with transformations with some of these. So what you do here is I would take here's my 2 to the x, here's my log base 2 of x, and we know x is positive is our domain. So what we're going to do is we're just going to take that and we're going to make it positive, right? Because graphically to try and do transformations on this would be a complete nightmare. So that's how you want to solve this to find your domain. Just go ahead and take that value in there and make it positive and then solve it. Well, let's find our critical points here. Our critical points would be our zeros. So what makes the numerator 0? Negative 2. So negative 2 would be on our testing interval. Negative 2. I cannot include negative 2 because if I plug it in, I'd have negative 2 plus 2 over 2 minus negative 2. Is that greater than 0? Well, I have 0 over 4. Is 0 greater than 0? False. So I'm not going to include negative 2. So that's our first critical point. Our next one is, where is this thing undefined? Well, if the denominator is 0, this will be undefined. Let me add x to both sides, so x equals 2. 2 would be my other one. I can't include it because it'll make it undefined. Now what I'm going to do is I'm going to test like negative 3. And let's see if it's true. If I plug negative 3 in for x, I got negative 1 over 5. Is that greater than 0? I say false. No, it's not. Now let's test something between negative 2 and 2. How about 0? 0 plus 2 over 2 minus 0. Is that greater than 0? Well, 2 over 2 is 1. Is 1 greater than 0? Yes, it is. That's true. Now let's test like 3. Let's throw 3 in to 3 over 2 minus 3. Is that greater than 0? 5 over negative 1. Is negative 5 greater than 0? False. No, it's not. So our domain is just between negative 2 and 2. Not including negative 2, not including 2. That's how you find your domain on that. All right, let's go ahead and graph using transformations. If you remember, log base 3 of x looks kind of like that. Here's our log base, or I'm sorry, here's our 3 to the x. the parent function here is log. So here's log base 3 of x. It's inverse. Instead of 0, 1, I got 1, 0. Instead of 1, 3, I got 3, 1, and so on. So here's our log base 3 of x. That's our parent function, which has a vertical asymptote of x equaling 0. Its domain is x greater than 0. Its range is negative infinity, positive infinity. So what does that minus 4 do? Well, that's going to horizontal shift it right 4. So instead of x equaling 0 being the vertical asymptote, I move that right 4. And here's our new vertical asymptote of x equaling 4. Instead of the point 1, 0, I move that point to the right, and I have 5, 0. So I moved it right 4, and I could draw it the same. So what would our x-intercept be? It'd be 5. 5, 0. That would be our new x-intercept, right? If you weren't sure, you could always plug some points in. Like if you plugged in 5, for example, log base 3 of 5 minus 4, log base 3 of 1. Let me write it this way. Log base 3 of 1 equals y. So 3 to the y equals 1. Well, what would y be? That'd be 0. 3 to 0 is 1. So y is 0. 5, 0, right? All right, let's do some more here. How about log base 2? So here's the graph of log base 2 of x, which goes through that point 1, 0, has a vertical asymptote of x being 0. So what would the negative in front do? First of all, that would be a reflection about the x-axis. So now we still have 1, 0, but we flipped everything around. And so we would be looking like this now, reflected about the x-axis. And then number 2, we will horizontally shift that left 3. So I take the whole thing, 1, 2, 3. The vertical asymptote of x equals 0 becomes x equals negative 3. There's our vertical asymptote. X equals negative 3. And that point 1, 0 goes left 3. 1, 2, 3. And becomes negative 2, 0. And the rest of it is the same. So there's our x-intercept, negative 2, 0. Right? Our domain here is from negative 3 on. Our range is all reals. Right? Negative infinity, positive infinity would be our range. About the natural log. Well, if you remember, here's our e to the x, right? Here's e to the x, so its inverse would be log base e of x. But again, that is the natural log of x. Log base e is the natural log. So it has the point 1, 0, has the vertical asymptote x equaling 0. So what about this? Well, I want to write that as natural log of negative x plus 1. And then what I'm going to do is I'm going to factor out a negative so I can see these transformations. I should make that a bracket. So what I have is the natural log of negative x minus 1. This will show us our transformations. So number 1 is I'm going to have a reflection about the y-axis. Okay, so starting instead of 1, 0, flip it over, negative 1, 0. And so I look like that now. Yeah, I still have the vertical asymptote x equals 0, but I've just reflected it about the y-axis. And then number 2, I'm going to shift it right 1. So instead of x equaling 0, x equaling 1 now is my vertical asymptote, and everything else looks the same. And there's our natural log of 1 minus x. How about this one? This is nicely showing our transformations. Notice there's no base shown, so this is log base 10 of x that's shown, goes through 1, 0, and it goes down, right? As that vertical asymptote x equals 0. So let's do number 1. We're going to reflect it about the x-axis, put the negative in front. So now it'll look like this, reflected about the x-axis. Number 2, now we're going to reflect it about the y-axis. So instead of 1, 0, I got negative 1, 0. So now we're like this. If I could draw that the same, there's number 2. And finally, number 3, we're going to move it left 2. So 1, 2 to the left. Everything else the same. Left 2. So instead of, draw that very good. Instead of x being 0, now I've got a vertical asymptote of x equals negative 2, but everything else the same. So vertical asymptote of x being negative 2. Our domain is from negative infinity up to that negative 2. Our range would be negative infinity, positive infinity. Let's solve some now that we've taken a look at them visually. Now that we've changed them from logarithmic to exponential form. We've also looked at them visually. We've recognized that logarithms are inverses of exponentials, right? But let's go ahead and solve some now for x. Notice that this is log base 5 of x, so I'm just going to put this in exponential form by going 5 to the third equals x, right? 5 to the third equals x. Well, 5 to the third is 125, so 125 is my x. I just solve for x. That's all I got to do. What's the x value that makes that true? In other words, log base 5 of 125 is 3, right? That's what it's saying. Let's solve for x here. Now it's my base. So here I'm going to go to exponential form on this. I'm going to go x to the third equals 1/8. I'm going to solve for x. So I got to take a third root of that, both sides, third root. So x is the third root of 1/8. Well, the third root of 1 over the third root of 8. Third root of 1 is 1, third root of 8, 2 times 2 times 2, right? I have 3 2s, so that'd be 2. So x has got to be a half on that. All right, how about this one? Change this to exponential form. 4 squared equals that x squared plus 9. So we got 16 is x squared plus 9. I go ahead and subtract 9 on both sides, and I have 7. And then I square root. X is plus or minus the square root of 7. Let's put this in exponential form. 5 squared equals 4x plus 5. So 25 equals 4x plus 5. I subtract 5 on both sides. I got 20. Divide by 4. It looks like I got 5. Here I got 1/2 to the third equals 3x minus 7. So 1 to the third over 2 to the third. Let me add 7 to both sides. So it looks like I have, what is that, 57 eighths. Yeah, 7 plus 1/8, 57 eighths equals 3x, or 3x equals 57 eighths. Let me divide by 3, both sides. So I get 57 over 24. How about e to the x plus 5 equals 4? Well, I would go ahead and put this in logarithmic form. So I go e to the x plus 5 equals 4. And remember, log base e is the same as the natural log of 4. Natural log of 4, that's just some number. So we're just solving for x now. So subtract 5 on both sides. So x is the natural log of 4 minus 5. That's what our x value is. And that'll kind of get you started on solving some logarithmic equations. Thanks so much for watching. See you next time.